Good afternoon, dear students. Today we will give an introduction for partitioning mechanism. But in order to understand partitioning mechanism deeply, we have first to mention some strategies by which we can change the mood of silica. As you know that silica has silanol groups. Now these silanol groups are polar groups. Okay. So in order to have a partitioning, we have to convert this solid to liquid. Okay. At the beginning, you cannot understand what we exactly mean that the stationary phase is liquid. Still, we use silica as solid support, but we derivatize silica. We change the nature of the silica. In 1970s, they add to the top of the silica, they add just hydrocarbons like mineral oil. Okay? If we have mineral oil as a layer here, then we will have a partitioning mechanism that the molecules of analytes might, in this case, partitionate between the mobile phase and the organic layer of the stationary phase. Okay. The problem with this physical coating that nothing can fix the stationary phase over the solid support, which is silica here. By time being, the mineral oil will be bleeded. Okay. And we cannot use the column for a long time period or for several injections. We just use it for a few times. The reason, as I said, that the liquid layer will be removed by time being. So they think to fix this problem by adding the organic layer here as chemical derivatization with chemical reaction. Okay. So they have several kinds of hydrocarbons. Now we have long hydrocarbons, okay, like C8, which is a chain of carbon, 8 carbons. We call it octane, or C18, octadecane, octa from 8, decane from 10. So we might use C8, octane, or octadecane, C18. Now the natural source of C8 is gasoline. We call it in Arabic benzene. Okay, car gasoline. C18 اللي هو C18 is the main constituents of diesel. So we can obtain these two material or two compound cheaply from oil. Now they add silicon head. Now this silicon head, it has methyl and halogen. Halogens such as chlorine. I guess you remember Williamson reaction for eterification. Williamson reaction in organic chemistry, that if you have alcohol, you can get alcohol ionized in strong alkaline media such as sodium, using sodium metal. So you will obtain alkoxide. Now alkoxide, if you react it with alkyl halide, okay, the attack will be here, the chlorophilic attack, and the chlor will be removed. So you end up with what? With ether. So that's why we call this kind of reaction Williamson reaction, to synthesize ether compounds. The same idea we will use it here, that silanol, instead of using strong base, we can use just naive base, because if you remember that silanol are acidic and they are isoster of carboxylic acid. Okay, so they can be easily ionized. So we just remove hydrogen in mild alkaline medium. Now this anion will attack silicon and the chlor will be removed. So we remove hydrogen and the chlor. The chlor and hydrogen will leave the reaction, will be elaborated from the reaction. So according to the Lachelier principle or mass action principle, once we have reactant and the product, if we remove one of the product, the reaction will be obliged to go forward. It becomes what spontaneous reaction. The same thing if we add extra amount of reactant in excess, also the rate of the reaction will move forward. The same idea that here HCl should be evaporated from the reaction. So instead of having reversible reaction, we will have a spontaneous reaction. We will end up with silicon attached with what? Oxygen with silicon head of hydrocarbon. Okay. Now the most important thing that the silica layer will be covered with hydrocarbons. Now these hydrocarbons, if we use aqueous mobile phase, as you know that the stationary phase and mobile phase, more or less they should be opposite. They are orthogonal. So we use aqueous mobile phase. Now once we have water, in addition, for example, to methanol in the mobile phase, now we will have what here? Hydrophobic interaction. Now, hydrophobic interaction is not enthalpic interaction. It is honestly entropy interaction because water molecule hates hydrocarbon. Water will make an arrangement, quasi-like structure. Okay, this arrangement of hydrogen to reduce the surface area of contact between water, and hydrocarbon. Now hydrocarbon will aggregate together and they form more or less hydrophobic interaction. But the resultant of this interaction is not enthalpic, it's not London force. It is in reality, London force is very weak. We have enthalpic, but it is very weak. But the main theme of the interaction is entropic because water tries to order itself. Water molecules order themselves in order to isolate hydrocarbons. We end up with what? With hydrocarbon aggregation. That's why we call it hydrophobic interaction. Okay. Now, this hydrophobic interaction make hydrocarbons as what? As layer over silica. But this layer is chemically interacted with what? With stationary phase. So it cannot be bleeded easily. It is very tough with covalent bond formation. And in this case, the compound will partitionate between the liquid over the stationary phase, okay, and it is part of the stationary phase, as well as the mobile phase. Mobile phase, it is liquid or fluid, such as gas. So we have fluid here and we have fluid here. So the compound, the analyte, will partitionate between these two fluids. Now this mechanism is partitioning, and according to the partitioning coefficient, the molecule may prefer to stay longer in organic layer or stay longer in aqueous layer. I will give you example to understand what do we mean here. If we have benzene and xylene. Now xylene, such as metaxylene, is more hydrophobic than benzene. So xylene will stay longer in organic layer of the stationary phase. So we convert also the theme of the partition. Instead of using silica, which is hydrophilic, we use hydrophobic stationary phase. Okay, and the mobile phase should be what? Should be aqueous. For example, large quantity of water with little amount of methanol or acetonitrile, CH3 C triple bond N. We call this acetonitrile. Okay. Now these are organic modifiers. We use one of them as organic modifier. The reason, as you know, in order to have a competition, the stationary phase should not be completely opposite to the mobile phase. We have to have some shared character between the mobile phase and stationary phase. That's why we use organic modifier. Now, the advantage of this kind of chromatography that we don't use hazardous mobile phase like normal phase. When we use silica, we use hexane, chloroform, etc. But here we use water. We might use, instead of methanol a little bit toxic, we might use ethanol. So, and cheap solvents. Okay. So this kind of chromatography relies on partitioning mechanism, and we call it reversed phase. Why reversed phase? Because the normal phase when we use silica, but here we change the order. Instead of having mobile phase as organic and the stationary phase as silica, which is normal phase, we change the order that the stationary phase is non-polar, whereas the mobile phase is polar. And we call this reversed phase chromatography. The mechanism of reversed phase chromatography is partitioning. Okay. So we will go back now to our example that xylene is more hydrophobic than benzene, so it will stay longer in stationary phase, in hydrophobic stationary phase. So benzene will elute first with mobile phase. After that, xylene will be eluted, and the mechanism will be more interestingly if we have significant difference in terms of partitioning coefficient among the analytes. For example, if we have xylene and we have, for example, resorcinol, one of the phenols. We have now, this is quite hydrophilic, this is quite hydrophobic. So we expect that resorcinol will be eluted before xylene. And this is a big advantage for partitioning mechanism, that it is applicable in reverse phase chromatography, and reverse phase chromatography is the most versatile technique, particularly in HPLC. HPLC, we will elaborate this terminology later on, and we will discuss it thoroughly with all its aspects. Okay, so we will finish now the part of the derivatization and partitioning, and later on we will continue to give more details about the derivatization and the limitation of the derivatization, and the treatment of the column with several techniques in order to reduce the outcomes generated from the degree of derivatization of columns.